But we have the pleasure today of hearing from Dr. Alyssa Rhoden, who's a staff scientist and group leader at the Southwest Research Institute in Boulder. And she's had many experiences working on many and serving on many NASA and National Academies committees. She's an expert in geophysical and dynamical processes of outer solar system moons, particularly candidate ocean worlds. And we're excited to hear from her today as she speaks to us about the heat signatures of ocean worlds.
Great. Thank you, Kate, so much for the introduction and for the invitation to speak with all of you today. I'll go ahead and share my screen. Here we go. Presentation mode. All right. So as Kate said, I'm here today to talk about the heat signatures of ocean worlds. And I didn't bother to list everyone who's contributed to all of the things I'm going to talk about because it would be a whole slide on its own. But there are definitely a lot of people who contribute to these projects. And I just wanted to acknowledge them. We also are supported by NASA's PSIE program and some internal funds from Southwest Research Institute. So over the past couple of decades, we've learned that the outer solar system may have many ocean worlds. Some of these are confirmed, which I've shown in the green, the blue check marks. Some are candidate ocean worlds, which I've highlighted in the white boxes. And some of these moons may not have oceans today, but did so in the past. Across, the decadal survey and, the astrobiology priority documents, detecting oceans is a high priority for NASA science, but it's actually a very tricky thing to do. And then characterizing the habitability of oceans, specifically the thickness of the ice shell and how much material can be transported across that ice shell, is even more challenging to do from remote sensing. More specifically, we have found oceans through a variety of mechanisms. The first is the induced magnetic field, which worked really nicely at Jupiter to detect the ocean in Europa and provide some evidence of an ocean in Ganymede. However, induced magnetic fields are not applicable to all bodies. So when we go to other places like Saturn, it's not as viable. So there we've used things like physical vibration and shape and gravity science to try to detect oceans. And we have a pretty solid case for an ocean in Enceladus. There's a lot of evidence for Mimas and maybe even Dione. But thinking forward to Uranus, where we really want to be able to explore oceans in all of the 5 mid-sized moons around Uranus, we really need to be thinking about what can be done there. And in particular, these are going to be cost-constrained missions. Going to Uranus has a lot of different types of objectives and different components to the system that we want to be looking at. And so we really need to be thinking about easy ways that we can do ocean detection. And so that brought me to this sort of overarching question of, can we use surface heat flow to answer key questions about ocean worlds? And today I'm going to talk about three icy moons. First, Europa, where we're pretty sure we have an ocean, but we'd like to understand more about the depth to that ocean. So what is the thickness of the ice shell? How does it vary? What processes is it involved with? At Mimas, which I've shown in the center, like I said, we have a bunch of evidence that there's an ocean within Mimas today, but a lot of it is model dependent, and we could still use some direct measurements to confirm the presence of an ocean in Mimas. And then the last one I'm going to talk about is Miranda, a moon of Uranus, where we really don't know if Miranda has an ocean today, when it last had an ocean, and that's a question that we would like to be able to address potentially with heat flow. All right, so as I said already, and probably no surprise to people on this call, we are pretty sure that Europa has a subsurface ocean, but we're a lot less sure about the thickness of that ocean and how much it varies across the surface. And the ice shell thickness can affect things like material transport, which then changes how we interpret our remote sensing measurements. Is that stuff on the surface coming from the ocean or not? And it gives us information about the viability of a habitat within the ocean of Europa. So here we want to use knowledge of Europa's thermal budget to make predictions of Europa's ice shell thickness in order to support future exploration with Europa Clipper. So what controls ice shell thickness on a moon? Well, the first thing I'm going to talk about is the amount of tidal heating generated in the shell. And this is generally, for Europa, being generated by an eccentric orbit. And so I've shown that here on the left. This is very much not to scale, but it's showing Europa going around in its eccentric orbit. So during part of the orbit, it's much closer to Jupiter than average. And so the tidal bulge is larger. So it's being elongated in the direction of Jupiter. And later on, you'll hear me use the phrase tidal axis. And that's what I'm talking about, is that line of longitude that's pointing toward Jupiter. And then later in the orbit, as Europa's further away, the tidal bulge is smaller. And so you get this flexing of the whole global shape. So tidal deformation is what's generating tidal heating. And the pattern of that is illustrated on the right from a figure from James Roberts' paper back in 2015. This is a very generic tidal heating pattern where you get the most deformation and thus the most heat at the poles, and you get the least heat right along this tidal axis. And so if everything else were equal and we only thought about ice shell thickness as a function of tidal heat, we would expect the ice shell to be thinnest at the poles and thickest at the equator along the tidal axis. A second thing that controls ice shell thickness is the thermal profile in the ice shell. And this is set by the surface and basal temperatures. So on the left, I am showing an interpretive map of surface temperature. This comes from Galileo data. And then on the right, I'm showing a couple of, cartoon thermal profiles. This is thinking about the difference in surface temperature. So if you're going through the ice shell and you make the assumption that the ice-ocean interface is going to be at the melt temperature of about 273 Kelvin, then if you have a warm surface, you have a fairly shallow slope of temperature gradient. And if you have a cold surface, you have a much steeper slope. And this is important because a steeper thermal gradient will actually conduct heat out more efficiently. And that means that the ice shell can remain thicker because it can conduct the heat out instead of melting. So all other things being equal, the ice shell will be thickest at the pole and thinnest at the equator based on the thermal profile. So you may recall from the previous slide, this is in contrast to tides. So tides will say you'll be thinnest at the pole, and the surface temperature effect would make it thickest at the pole. So one of the things that we're really interested in our exploration of Europa is understanding which of these characteristics dominate the ultimate pattern of ice shell thickness and heat flow on Europa. But we're not done yet. There is one more thing that really affects ice shell thickness, and that's the amount of heat we assume is entering the ice shell from the deeper interior. We call this the basal heat flux or heat flow. And here I've illustrated 3 options on the left that we included in our study. So we used constant basal heat fluxes for a low, medium, and high amount of heat. And this is a major unknown, the basal heat flux. There are many sources that we can consider, including tidal heating in the ocean, radiogenic heating from the rocky interior, and potentially even tidal heating from the rocky interior if it has a high porosity, which is expected for Enceladus much more so than for Europa. It's also possible that the basal heat flux is not constant everywhere because the ocean itself can move heat from the bottom of the ocean to the top of the ocean. It may distribute the heat in a spatially variable way. And while we haven't done that for Europa yet, I've thrown in a little cartoon of what that might look like based on some models of ocean circulation. So in order to predict Europa's ice shell thickness and understand what surface heat flux could be telling us about the interior of Europa, we combined a tidal heating model. In this case, we used a model called MATH, which has been out for a few years now and can do pretty sophisticated tidal heating, and also can adopt an arbitrary number of layers within the ice shell. And so we can actually put in conductive ice shells and we can do all kinds of fun stuff. So we're taking our tidal heating model, we're coupling that with a model of Europa's surface temperature, and then we're exploring different values of basal heat flux. And we're using these 3 things in order to calculate the equilibrium ice shell thickness at multiple locations on Europa and the surface heat flux that's associated with that thickness. And from that, we've created contour maps of shell thickness and surface heat flow for each of these values of basal heat flux. But to get us oriented with how to look at the output and the maps that I'm going to be talking about today, we're going to start with just a constant surface temperature. So forget this middle map. We're just going to make it all 100 Kelvin and see what we get. Okay, so on the left here, the purple plots are showing the ice shell thickness that we're producing from this project. On the right, the blue and red are showing the surface heat flux. So thickness on the left, heat flux on the right. And then the rows are the amount of basal heat flux that we're assuming, where the upper row is 1 milliwatt per meter squared, the middle is 10, and the bottom is a pretty high heat flow of 50 milliwatts per meter squared. And again, this is the extra heat that we are applying to the bottom of the ice shell, okay? And what we see is about what we would expect. So the heat flux and the ice shell thickness both follow the tidal pattern. So where tidal heating is high, we get thin ice, so that's up here by the poles, and we get high heat fluxes, okay? And that's true across all of these basal heat flows. The other thing that's really interesting here is that when we go to very high basal heat fluxes, the variation in ice shell thickness or surface heat flux are reduced. And the reason is that the tidal heating has stayed the same. The amount of heat flux coming from tides is the same in all of these cases. When that tidal heat flux is relatively small compared to the uniform basal flux, then the pattern becomes more uniform, more like the basal flux. When the basal flux is low, like in the upper panels, the tidal heat dominates, and so you get much more of a tidal pattern. It's worth pointing out too that each of these scale bars shows pretty wide variation, and some of these upper thicknesses would almost certainly be convecting. So our model of conductive ice would break down here. So these are a bit idealized. It's also the case that we are not accounting for any lateral flow of heat or ice in these cases. So these are the largest thickness variations that one might predict. But getting back to our initial question of like, well, what happens when you take realistic surface heat fluxes? We get pretty different patterns. So in these cases, each location where we computed tidal heating, we also applied the actual surface temperature from that model in order to get a more realistic thickness and surface heat flux. Based on the grid that we used and the data that's available, some of the south polar data is not available. So these gray areas are where we didn't have a surface temperature. So we just excluded those locations from the map. And what we see here is really, I find really fascinating, which is that the shell thickness is more sensitive to the surface temperature than to the tidal heating pattern. And so now we get our thinnest ice shell at mid-latitudes in between the 7 anti-Jupiter points. Okay, so, and if you get higher basal heat fluxes, they get thinner, but the locations don't change. So if we were predicting where Europa's ice shell will be thinnest today, it would not be at the poles. Interestingly, the surface heat flux does continue to follow the tidal heating pattern. And the reason is that the amount of heat that can be conducted out of the ice shell is pretty consistent. It just depends on how thick the ice shell could be in order to conduct out that same amount of heat. And again, we do see that you have less variation in ice shell thickness when the basal heating is dominating the thermal budget. Across all of these cases, the biggest unknown is how much basal heating we have. As you can see here, we move from ice shells that are tens of kilometers thick to an ice shell that's 15 kilometers thick. Okay, so wrapping up some of the Europa work, this paper came out a few months ago, and we did a lot of different kind of neat things related to surface heat flow at Europa. So I encourage you to check this out if it's something of interest to you. So in addition to the work I just showed, we also derived what precision you would need on heat flow measurements in order to constrain the thickness of Europa's ice shell. And what we found is that about a 5% uncertainty in the heat flow measurement enables you to constrain the ice shell to within 2 kilometers or better everywhere. So places where we expect higher heat flows, you can get tighter constraints for the same uncertainty. The spatial resolution of the temperature data also matters. If you have very large surface temperature footprints, you're going to swamp out some of the variability in ice shell thickness. And then, unfortunately, it's not likely that we can capture this information with e-Themis data, assuming that we're using just the magnitude. The increase in the increase in the radiation, the radiative flux that e-Themis would measure will not be sensitive enough to do this. But we may be able to get clever with things like timing and location, looking at how the data changes over Europa's surface, and that might be able to help us get at these numbers. We also produced some thermal gradients that include tidal warming of the deeper ice shell. So when you have a conductive thermal profile through the ice shell, tides actually warm close to the bottom of that shell, and they can create an isothermal base to the shell, which is a little bit reminiscent of a convecting ice shell, but you don't actually need to stimulate convection, you just need tides. So some interesting work that might have implications for some of our geologic models. In the future, we would like to incorporate lateral flow of heat and ice and really get at how long these variations could last. We'd like to apply variable basal heat flows, and we'd like to look at obliquity tidal heating and see if that changes the pattern of heat flow at all. In the meantime, the Juno mission has returned some data that might help us ground our models. No pun intended with that. Okay, so at DPS EPSC in Finland, just back in September, Steve Levin presented some of the preliminary results from the Juno MWR, which observed Europa. You can see on the upper right panel, the location. So this was always in the same quadrant of Europa where they took their data. And each of these channels probes to a different depth. And by stacking all of these profiles, they're able to derive a shell, a thermal profile for the ice shell, and then from there derive a thickness. Okay, and so this bottom panel is also from Steve's talk, where they say that the ice shell is 29 kilometers plus or minus 10. Now they're saying a thermally conductive ice shell is 29. That's because the MWR can't sense if there would be a convecting layer underneath. For our models, we always use a conductive ice shell, so we're making the whole thing conductive. So we started with this assumption that the ice shell is 29 plus or minus 10 kilometers thick. And because of that, we can then tune our basal heat flux to fit that thickness at the location of the Juno measurements. And then we apply that same basal heat flux everywhere, and we build a global map to see how much variation in ice shell thickness we would predict based on this measurement. So I do want to note that this study is preliminary. These results may change once the actual paper comes out. And we need to be able to compare things like what thermal profile they are assuming in order to link MWR data to a thickness versus what thermal profile we're doing to make sure that these are self-consistent. But in any case, just for fun, I'm reporting here the 3 thicknesses that are consistent with the data, and then what basal heat flux we would need in order to make that thickness stable. And then we make a little map. So here we again are using our variable surface temperatures from Galileo. We're using a thickness of 29 kilometers that then sets our basal heat flux. I put some black lines around this region where Juno took its data. So unfortunately, it's like not in the center of the image, but it's basically the same as what we see over here. So in this region, we would expect the average to be 29 kilometers. And then you can see that as with our previous models, the thinnest regions are off the tidal axis and at mid-latitudes. The ice shell will thicken as you go toward the poles due to the surface temperature effect. And the range of ice shell thicknesses is about 20 to 30 kilometers. And these thicknesses would correspond to surface heat flows of 20 to 30 milliwatts per meter squared. We also did the thinner ice shell just to see what happens. In order to keep this ice shell 19 kilometers thick in the region of interest, we have to increase the basal heat flux to 25 milliwatts per meter squared. And at that point, it is starting to reduce the tidal heating pattern in this thickness. So you get more uniform thicknesses. So wider patches of relatively thinner ice. The other interesting thing that happens is that things tend to be shifted more toward thicker shells than this location. So we end up with a range of 16 to 25 kilometers thick. Okay, so just to summarize what we found for Europa, we find that heat flow and surface temperature measurements can constrain ice shell thickness when they're taken together. And the differences are small. So we would probably need to be proactive and creative about coming up with a campaign to measure heat flow and surface temperature in a way that allows us to really constrain the ice shell thickness. But if we do that, we can be getting information down to like the kilometer scale. Moving on now to Mimas, where we were really interested in this idea of a present-day ocean. So Mimas has a large libration. This is an oscillation of Mimas relative to the direction of Saturn. And it was best explained by an ocean, although the original measurement could also be explained by an elongated core inside a frozen body. However, analysis of Mimas's pericenter precession strongly favors an internal ocean. And in fact, they found that if you wanted to explain the precession with an elongated core, it would be so elongated that it should stick out of the icy mantle, which we don't think we see. So the ocean has become the leading candidate for explaining what's going on with Mimas. But we would sure like to know whether surface heat flow could further constrain the interior and particularly tell between a frozen case and an ocean case. And we did some work back in 2022 to look at the globally averaged tide within Mimas and just look at it as from an average perspective. Like, what would it take to get this 20 to 30 kilometer thick ice shell to be stable over an ocean within Mimas? And one of the things we found is that when we produced a frozen interior, the surface heat flow was smaller than the radiogenic heat flux we assume is going in from the core. So whatever we assume is entering the ice shell from below then has to transit the ice shell, which is getting larger and larger in volume as you move outward. And so the surface ends up being pretty low. So we got something less than 6 milliwatts per meter squared. If we had made different assumptions about what was entering the ice shell from below, you could get even smaller values of surface heat flux. And then we did the same thing with an ocean where we looked at different basal heat flows at the base of the shell. We looked at a 20 to 30 kilometer thick shell, that's our goal, and then we calculated the surface heat flow. And so this figure summarizes the findings. So we have different shell thicknesses along the x-axis, we have different heat fluxes along with the y-axis. The blue dots are the basal flux, so this is how much we need to enter the ice shell from below, and then the orange dots are how much comes out of the surface. So in order to get a 20 to 30 kilometer thick shell, which is consistent with the observational evidence, we need pretty low basal heat fluxes actually, so less than 2 milliwatts per meter squared entering the base of the shell. And the surface heat flows we get vary from 20 to 30 milliwatts per meter squared. So these results suggest that maybe the surface heat flux could be telling us something about the interior and the ice shell thickness, the presence of an ocean. However, our measurements would be local, right? We would send a spacecraft and it would look at a region, not global. And so we don't want to be relying on globally averaged predictions in order to do this. So just like with the Europa case, we used a tidal heating model. Here we used an idealized surface temperature that accounts for the fact that the poles are much colder. And we included a variable basal heat flux assumption in addition to a low and a mid-range basal heat flux. And then we again create maps of surface heat flow and ice shell thickness using these models. So this is a bit more complex because we have now also the variable heat flow. So the upper panels show the surface heat flux, which you can see gets pretty high. Your Mimas has a very high tide. So as soon as you have an ocean in Mimas, this thing goes off. The bottom panel shows ice shell thickness. And again, these variations in ice shell thickness are maxima. If we were tracking the flow of heat and the flow of ductile ice, these variations would smooth out somewhat. But what's really interesting is the pattern, right? So we can create several different kinds of patterns with different locations of higher heat flux and lower heat flux. And really the coolest part is that we again see these mid-latitude thin regions, which is not the same as the tidal pattern. So the simple case of like, whatever the tidal pattern is, that's what the thickness should be. This is just not very realistic given the surface temperatures. Okay, so if we wanted to create a measurement requirement to find oceans at Mimas, the answer would differ between whether we use a globally averaged model or a spatially variable model. So with a global average, the heat flow in the ocean case is about 2 times that of the frozen case. And for the inferred ice shell thickness of 20 to 30 kilometers, you get things that are closer to 30 to 20 respectively, which is considerably higher, like factor of 5 higher than the frozen case. So even in the global average model, we would expect to be able to detect an ocean as compared with a frozen case. If we go to spatial variable models, we get much different answers, in that the surface heat flux can be considerably higher, like an order of magnitude higher than the frozen case, even if the basal flux is very low. We see that the heat flows will vary with latitude and to the lesser extent longitude. So doing some kind of noodle across the surface might be really helpful in pinpointing things like what is the basal heat flux and how much does the ice shell thickness vary. So if we wanted to do this, we would need sensitivity in surface heat flux of, a few to 10 milliwatts per meter squared. All right, so moving to Miranda, this is the moon that we probably know the least about in this trio. So the geologic activity, you can see a lot of odd surface features in this image. The geologic activity suggests recent internal heating, but the present day eccentricity is extremely low. And that might even indicate some dissipation through orbit circularization. And that means that there could have been an ocean in the past that enabled these features to form, and then it froze out as the orbit circularized. But we really don't know. As people have been thinking about the Uranus orbiter and probe mission, they've been quantifying how easy or hard it would be to do ocean detection from various methods. And some papers have come out showing that libration and obliquity are probably not going to be sensitive enough to do ocean detection at Miranda. And the mission is not going to orbit Miranda. So that's going to really limit any studies of gravity and tides for ocean detection. So this is why we're really interested in understanding whether heat flow is viable here. So Miranda, where we know so little, we're really probing a bunch of things: the presence, age, and depth of an ocean. And so for this set of models, we assumed just an average temperature of 60 Kelvin at the surface. We used a globally average tide, and we're just trying to get a very general idea of the difference between these possible models for Miranda. So one is that Miranda had an ocean long, long ago. It has since frozen, the interior has cooled, and so the interface temperature between the rocky interior and the ice shell, we're making a pretty chilly 100 Kelvin. Then we have a case where we're assuming that the ocean was fairly recent, and while it has frozen out, the interior is still warm. So the base temperature is closer to the melting temperature, something like 250 Kelvin. And then we have our two ocean models where we keep the base temperature constant, but we make different assumptions about how thick the ice shell is going to be. So we have a very thick ice shell over here, we have a thinner ice shell over here. And the big difference between them is how much basal heat flux we have to assume is entering the ice shell in order to keep these thicknesses stable. And again, the current eccentricity of Miranda is very low. So tidal heating is basically negligible for Miranda at the present day. And that means that if you wanted to maintain a present day ocean, you would need 20 to 25 milliwatts per meter squared just from the rocky interior. However, Miranda likely had a higher eccentricity in the past, perhaps even in the last 10 to 100 million years. And so that would reduce how much basal heat flux we require in order to replicate these results. Okay, so for the frozen cases, we find that the surface heat flows are pretty small, 1 to 3 or maybe even less, depending on how much of that basal heat flux we're assuming. When we add an ocean, they go up by a factor of a few. So with a very, very thick shell, they're starting to get close to the same as a frozen but warm shell. So these two might be a little bit hard to tell the difference between. But once you start to thin the ice shell, even to something like 70 kilometers thick, you're getting a factor of 3 difference from a frozen case. So the inferred measurement requirements for oceans at Miranda, a little bit different. So the heat flow in ocean versus frozen cases can deviate by an order of magnitude. But if the ice shell is very thick, the heat flows are going to be similar, whether they're frozen and warm or whether there's an ocean. So for that, you'd probably want some kind of secondary analysis, like a libration measurement, which even if on its own it can't tell the difference between these two, maybe as a combination, you could. We see a factor of 2 to 6 deviation in heat flow across different ice shell thicknesses. And there's a very low heat flow for all the frozen cases. So that means it would be pretty hard to tell the difference between a warm frozen ice shell versus a cold frozen ice shell, as everything is pretty low. So for this ocean detection, we have less than 3 versus greater than 7. If we wanted to constrain shell thickness, we would need to be at that 1 to 3 milliwatt per meter squared precision level. And if we wanted to understand the thermal state of a frozen shell, we would need something less than 1 milliwatt per meter squared precision. So all of this brings me to, is there an instrument that would actually allow us to take these measurements? So on the right, I'm showing the e-Themis performance metrics for Europa from the Christensen et al. Review paper. And so we have the surface temperature that's anticipated at the body, and we have the temperature increase that's anticipated due to a particular amount of endogenic heat flux. So in addition to re-radiated sunlight, we're getting that emission caused by tidal heating and conduction through the ice shell. And each of these curves is a certain amount of heat flow that they're assuming is being pumped through the shell and out the surface. And you can see that they, even pretty high heat fluxes, like 150 milliwatts per meter squared, only raise the temperature by 4-ish Kelvin. Okay, so these are pretty small changes in the apparent temperature. And the noise levels are shown here for bands 2 and 3 in the red dotted lines. And the noise levels frequently are above the signal that we'd be looking for if the endogenic heat flux is relatively low. And it gets much worse for cold surface temperatures, which unfortunately for places like Miranda, the surface temperature is probably going to be in this lower end. Okay, so what we would need in order to do ocean detection is to be able to, measure in the range of 40 Kelvin to 90 Kelvin surface temperatures. And we're looking for heat flows that are probably 30 milliwatts per meter squared or less. Although potentially, if you were looking in specific regions of high activity, you would be able to see, higher heat fluxes. But our uncertainties are, 1 milliwatt per meter squared to maybe between 3 and 5, depending on the case that we're looking at. So this is hard, is really the takeaway. We know that this is going to be hard because Galileo PPR could not isolate the effects of the endogenic heat flow on Europa, even though we know that there's an ocean, and therefore there must be an endogenic heat flux from that ocean. And again, e-Themis is unlikely to detect the ocean-generated endogenic heat flux unless we get really clever about our observing strategy. The Juno MWR measurements seem promising, but we really need more lab data on the properties of ices in order to make sure that we're interpreting the reflections correctly. And then, it's going to take the paper to understand how the thermal profiles are being applied and really bring everything together. All right, so summarizing everything, as I said, for Europa, this could be promising if we had good enough precision as a method to constrain ice shell thickness and really map the thickness of the ice shell. For Mimas and Miranda, ocean detection is certainly possible with sufficient precision, but for the surface temperature reasons, it might actually be really hard. And I would say ocean detection is a lot more plausible than things like characterizing ice shell thickness, just because we're still, at the early stages of this inquiry. And with that, I will take questions.
Great. Thank you so much, Alyssa. Let's all thank Alyssa. Okay, there are several questions in the chat, which is great. And if you have more questions, feel free to go ahead and add those into the chat. Also, you can raise your hand and I'll call on you as we get to people who want to raise their hand and ask questions. Also, if you asked a question in the chat, but you'd prefer to vocalize it, I'll call on you as we get to those questions in the chat. And if you want to vocalize it, you can do that as well. So we'll start with a question in the chat from Paul. Paul, I'll give you a second if you want to unmute and ask it yourself, or I'll read it for you.
I can go ahead. Great stuff. Excellent. I'm wondering if you expect a topographic signature that can be detected on this, given that I'm working on the global shape model, but it's very difficult using the existing data, and we'll get better, of course, with Clipper. But do you expect a signature?
So I don't I'm not ready to answer that question yet, because you have to account for things like isostatic compensation and all of these kinds of things. But I'd be very happy to work with someone who does think about topography to be able to translate the ice shell thickness variations that we would be predicting with those types of models. I think the bigger issue is we haven't modeled the flow. And I think there are models out there. We just haven't been able to incorporate them into our results yet. But I think that's the biggest next step. Just see how persistent thickness variations can be on Europa before we try to make a global shape model.
Yeah, that was my secondary question as to whether the heat input would maintain any such variations against flow. So that would have to be worked out, as you say.
Yep.
Great, thanks, Paul. Ashley, you have your hand raised. Go ahead.
Sorry, a miscue on my part. I do not have a question.
Okay, no worries. Okay, plenty of questions in the chat. We'll go next with Al Emron. Do you want to unmute and ask your question?
Sure. Great talk, Alyssa. So I'm just wondering if is that possible that Europa's ice shell thickness can reach to nearly zero, meaning that ocean can be also very close to the surface, as it has been suggested and indicated by different geological feature, which is thought more of the recent feature, and also some compositional evidence by some data analysis. Does your heat flow model support those characteristics? Because you mentioned the thickness can be a few tens of kilometer plus minus something. So is that also possible? Heat flow model can also predict that ice shell thickness can be very close to zero, like the ocean can be very close.
Sure.
Close to the
So
surface.
based on the models that we've created, I would say heat flow alone is not going to thin the ice shell to a few kilometers or 1 kilometer or less than one. In order to do that, we would have to increase what we assume the basal heat flux is to a pretty high value. The challenge is, as you thin the ice shell, the amount of volume that can respond to tides and therefore generate heat from tides gets smaller and smaller. And so you have this trade between a thinner shell that maybe can flex more and the actual ice that's there to warm up. And so we are not finding that you would get a very thin shell. Now, that's not to say the shell is never thin. It's very possible that you have some secondary mechanism like fractures or some kind of localized enhanced melting, brine mobilization, all these fun things that we could add to say, you know, in one region you are maybe thinning more rapidly than another, or you're thickening more rapidly. There's a lot of other things you could add, but heat flow alone will not thin the shell unless you have an arbitrarily high background flux.
Thanks.
Great, thank you. I'm gonna take a moment and ask a question of my own. So, related to your model on Miranda, Alyssa, I was curious, and maybe I missed it. You know, there's been suggestions from recent works that the oceans in the Uranian system could be significantly colder due to, you know, antifreeze-like effects from the constituents in the oceans. Would that have a big effect on the results of your model?
So it might, but not in a helpful way, actually.
Yeah, that's what I thought maybe.
Yeah. So initially we thought, oh, wouldn't it be great if you had antifreeze in one of these oceans, and then you could change the thermal structure of the shell. So you would change the melt temperature of the shell. But what really also changes is the viscosity of the ice that's associated with a particular temperature. And so you have to be considering all of those things together when you're looking at how much tidal heating is deposited. And it generally does not help you make more heat where you want more heat. But maybe it could keep things from freezing. I don't really know. I don't really know. We've looked into this a little bit and realized quickly, one, it's very complicated because you really need a lot of lab work that asks the right questions, and everything is connected. So you can't just say, well, let's just lower the temperature and, you know, pretend that works. It's not realistic.
Okay, great, thank you. I definitely agree with more lab work needed. Love that. Okay. Next question, Amir Bagiri, do you want to unmute and ask?
Sure. Hi, Alyssa. Great talk. Yeah, just to add a bit of more complexity, do you assume that Europa is currently in thermal steady state? I'm trying to understand if you have to assume that for your calculations, and if
So
yeah.
Well, go ahead, finish your question.
No, that's almost, yeah, pretty much it.
Yeah, so in this case, for the results I reported for Europa, yes, we make the assumption that the ice shell is neither melting nor freezing. It is in thermal steady state. We know that over long periods of time, probably 100 million years, the eccentricity of Europa is varying periodically. And so you're going to go through phases where there would be more tidal heating or less tidal heating than the value that we're assuming today. So I think those changes are deeply interesting. So this idea that at some point you're going to be thickening the shell, and at some point you're going to be thinning the shell just from those variations. I then wonder if you have regions that are always thicker, are they changing more or less rapidly than regions that are always thinner? Those types of questions I think are really interesting, but they're much longer time scale. And some of the back of the envelope calculations we did suggested that the ice shell should be able to reach its steady state more rapidly than those changes are happening. But we also did look at long-term, how variations overall can affect the average thickness of the shell. And it does actually reduce the average thickness because you're kind of always trailing behind the variations.
Great, thanks.
Interesting, thank you. Next up, Mark Elowitz, would you like to unmute and ask your question?
Yes. Do you take into account the possibility that there might be non-water ice contaminants within the ice shell and the actual particular phase of the ice structure itself in the simulation?
So the second question is easier to answer. These are very low gravity bodies, especially the small guys, Mimas and Miranda. I tried to show everything roughly to scale. And so the phase of the ice is going to just be ice one. It doesn't go into high pressure phases at all. As for the composition, so in these models, yes, we used pure ice, no contaminants. But part of our PSIE project includes working with Jacob Buffo at Dartmouth and Christine McCarthy at Columbia. And so what we're doing with that team is trying to understand how the inclusion of salts changes the thermal structure, the viscosity structure, and then those things will change how much tidal heating you get and where in the ice shell it's dissipated. So that is future work that we are considering.
Okay, thanks.
Great, that sounds super exciting and also very necessary. Okay, next up, John Spencer, would you like to unmute and ask your question?
Sure. Yeah, Alyssa, great talk. So yeah, the old issue of Mimas and high heat flow and the damping time scale, and that's clearly the hard thing about having an ocean and these very high dissipation levels on Mimas. So can you remind us what those damping timescales are? And I think it's, tens of millions of years or something like that, right?
Yes, and actually, give me a moment. I'll see if I can open my DPS talk and I can just show you guys a fun graphic from that. Also, when I went to DPS, all my fonts got changed. So everyone who saw this talk saw it with like horrendous fonts that were way too big and no one could read anything. So this is like my moment, to show it really. Okay. So this is the main plot that was in our paper where we looked at the timescales. And so let me talk you through this. So we have eccentricity on the x-axis and it's decreasing as you go to the right because we're increasing in time. And the dissipation within Mimas is reducing the eccentricity. So you're circularizing the orbit. And then each of these colored lines represents the eccentricity that we assumed at the onset of melting. And so here we have 3 times the current eccentricity all the way to 2.5 times the current eccentricity. So we start off, we assume melting has just happened. So you have a very thick ice shell, almost the whole hydrosphere is ice. The eccentricity is very high, so you have very high dissipation. And so as you are melting the shell to get back to get to what what it would like to be the thickness of equilibrium, you're also reducing the eccentricity through dissipation. And so you get this nice curve that bottoms out around here. This is where the current eccentricity is. And then additional circularization and loss of eccentricity will lead to thickening and cooling and freezing of that ice shell. Okay, and so here in this table, I have the values that we found. So yes, 10 million years, 15 million years to get from the onset of melting down to the present day eccentricity and the thickness that we think we're observing. So yeah, the challenge with the Mimas ocean hypothesis is that the ocean has to be pretty young. People really don't like that. There's a very like anthropocenic objection that we are too new and unspecial and therefore should not see anything new or recent in the solar system. If the Mimas Ocean were the only weird and apparently recent thing going on in the outer solar system, I would agree. I would say this must be wrong. But we see, potentially a young ocean in Enceladus. We see rings of Saturn that seem to be evolving and maybe young or old, we don't know. And then when we go to a place like Miranda, we're seeing surface features that also appear to be relatively young. So something about the way these giant planets evolve, the way that their interiors evolve, seems to have a really strong effect on the orbital evolution of the moons, the amount of tidal dissipation they have, and when they get into and out of resonances with each other. And so I think we need to reframe our thinking to look at these moons as a continuum. So how are moons evolving with time? Where are they in the life cycle of an ocean? We should not expect to see them all at the end of their life cycles. We should expect to see some at the beginning, some in the middle, and some at the end, which I would argue that we do.
Okay, thank you.
Okay, great. That was great because also during that time you received several more questions. So awesome.
Oh, great.
Great discussion. Daniel Wenkert, do you want to ask your question? Unmute and ask your question.
Yeah, sure. We're looking at an instrument called Cobra for Uranus Orbiter, and I was wondering, given the specs that I put in the question, could that actually help constrain the ocean thickness on Miranda?
I mean, I would want to look at it in more detail and understand exactly how your wavelengths compare with depths and such. But yeah, I mean, that sounds like the kind of instrument that we'd be looking for. Certainly colder temperatures, that's going to be the critical piece.
Okay, thanks.
Yeah, if I can chip in there, the fact that you have this very large obliquity in the Uranian system, so things have there's long winters for things to get really cold. And for the heat flow to become more apparent is a nice advantage, definitely compared to Europa, where you have pretty constant sunlight, even very close to the poles.
Right. That's exactly the both the nice thing and the hard thing about Miranda, because yes, if you get there, you're going to have half the moon that's in darkness and will have been in darkness for a long time. And so you should be able to see the signal very clearly. But if your instrument is tuned to be most sensitive at warm temperatures, you'll be at a disadvantage because the surface will be very cold. So we need something that operates well in cold temperatures to find this signature.
Yeah, great points. Okay, Sean, Sue, would you like to ask your question?
Oh yeah, hi. Can you hear me?
Yes, we can hear you.
Yes, hi.
Great. Hi. So nice talk, and I just want to learn about how is this your model applied to Enceladus, and if you can share a few words. Thanks.
Yes, so we could do the same type of analysis at Enceladus. We haven't, mostly because heat flow has been measured at Enceladus by John and others, and so it didn't seem to be as necessary to try to understand all this. But we certainly could look at, whether the heat flow story is as consistent with the Cassini measurements as we're hoping it would be. So we certainly could apply it to Enceladus. Nothing particularly hard about that.
Great. And question from Duncan. Would you like to unmute and ask?
Yes. naturally throw a couple in there, but unrelated ones. But yeah, great talk. Have you looked at the effects of porosity variation in the surface affecting the conductivity and what impact that would be on this modeling approach?
Yes, so we discussed doing this. So when I say we, I mostly mean myself and Matt Walker at PSI, who developed the tidal heating tool that we're using. So we have thought about looking at an insulating layer on the surface, particularly actually for Enceladus, where we see high heat flows associated with relaxed craters. And so we expect that there is an insulating regolith. We haven't done that for these other moons just because we don't have as good of a reason to look at it. I will take the moment to mention, though, that for the surface temperature maps we used for Europa, we did not take those surface temperatures at the exact surface, but somewhat below the surface. And the goal was to get below the diurnal skin depth. So we're getting longer term temperatures than, you know, the morning or the afternoon.
Thanks. And then my second question was Herschel. Has there been work to see if Herschel can survive an ocean on Mimas?
Yes, so I would refer you to two papers by Denton and Rhoden. I think the first one was in 2023, and the second one just came out this past year. So in both of those papers, Dean Denton used IceSail to model the formation of Herschel with either a cold frozen interior or a warm frozen interior or an ocean bearing interior. And what we found was really interesting. So a very cold Mimas actually cannot reproduce Herschel's morphology. You get a very, very deep crater with steep walls and no interior topography. And we do see a central peak in Herschel, so we would not call that consistent. The other interesting thing we found, those papers are about the formation of Herschel. If you are interested in the preservation of Herschel, that's a relaxation question. So I'm going to forget her name. There's a graduate student at Purdue who's doing excellent work. I think her name is Mariana, but I don't remember the last name. She presented it also at DPS. So she's been modeling heat flow based on our paper, the heat flow over time, and looking at how much Herschel would relax. And what she has found is that she does not find that Herschel would relax based on the heat flows with an ocean that we created. So basically, there has not been enough time and high enough heat flow for Herschel to relax. And as Paul is putting in the chat, we don't see clear evidence of eddy relaxation. So yes, the long answer to your short question is Herschel can survive an ocean on Mimas, and in fact, may require an ocean to have formed with its current morphology.
Thanks.
Thank you, Kevin.
Perfect, yes. Okay, any last quick questions for Alyssa? This has been such a great discussion. Thank you, everyone, for all your great questions.
If there aren't questions, I want to throw out a shameless plug to a paper we just published in Nature Astronomy the Tuesday before Thanksgiving, so nobody saw it. This was a paper led by Max Rudolph, and in that paper we were looking at what happens when you grow an ocean for the first time in one of these small bodies. And what we found was that for Mimas, Enceladus, and Miranda, as you first begin to melt back the ice shell, instead of getting compressional failure, which we would expect on larger bodies, you actually can start to boil the surface of the ocean and create an atmosphere within the region between the ocean and the ice shell. And we're now looking into potentially driving convection and upward crack propagation based on the dynamics at that interface. So check it out if you have time.
Super cool. Yeah, sounds fun. Maybe we'll have to have Max come give a talk next year for the lecture series.
I'm
so yes,
sure
I
see. To do that.
Yes, I see your comment in the chat, Paul. I agree. It was so great to have this extra time and have a lot of good conversation and good discussion. So thank you, everyone, for that. Thank you again, Alyssa, so much for such a great talk and a great discussion afterwards. Everyone, have a great time at AGU. Have a great holiday season, and we will see you in 2026 for the next Europa Clipper lecture series. You can expect calendar placeholder invites from us in the coming weeks for 2026. So yes, happy holidays, everyone. Thanks to Kate, the co-organizer here, and for you all for attending and creating this.
Yeah, thank you all for being here.
Thanks, everyone.
Thanks again, Alyssa.
Great talk, Alyssa. Yay. Very nice. Happy holidays.
Thanks. Bye.
Bye, everyone.